Welcome back to our series on nanostructured materials, science and technology. I am Professor Ashutosh Tiwari from the Department of Material Science and Engineering at the University of Utah. In our first lecture, we explored the foundations of nanotechnology, what it is, where it came from, and why it is such a powerful field today. We talked about the atoms, the evolution of atomic theory, Richard Feynman's vision, and how nanomaterials are classified and applied in the real world. In the second lecture, we are going to build on that understanding by looking at one of the most important principles in nanoscience, scaling laws. These laws explain how physical properties change when the size of an object changes. As we will see, shrinking down to the nanoscale doesn't just make things smaller, it can completely transform how they behave. Let me start with a question. Why can a flea jump nearly 200 times its body length, while an elephant can't even jump at all? It is not about training or strength, it is about physics. This contrast is a perfect example of scaling laws in action. When we change the size of a system, whether it is an animal, a device, or a material, its geometry changes, and that changes how forces and energies act on. A flea, being tiny, has very little weight compared to the strength of its muscles. An elephant, on the other hand, it is so massive that gravity completely dominates, making jumping impossible. This difference between the flea and elephant is our doorway into the world of scaling laws. So what exactly are scaling laws? Scaling laws describe how physical properties change when we change the size or scale of an object. When you shrink or enlarge something, its geometry changes, and that directly affects its properties. And since properties determine performance, size ultimately controls how well a system works. At the nanoscale, these changes become dramatic and sometimes counterintuitive. Things we take for granted at our scale, like strength, weight, or even color, can behave in surprising ways when we go smaller. One of the most important scaling effects is the surface area to volume ratio. Let us compare two cubes, one with a side length of 3 centimeters and another just 1 centimeter. For the larger cube, the surface area is 54 square centimeters and the volume is 27 cubic centimeters. That gives rise to a surface to volume ratio of 2. For the smaller cube, the surface area is 6 square centimeters and volume is just 1 centimeter cube, giving a ratio of 6. So even though the cube is smaller, its surface area compared to its volume is much larger. This is a key principle in nanoscience. Smaller objects have more surface area relative to their volume, which means they interact more with their surroundings. That is why nanoparticles can be so reactive and why their properties differ so dramatically from bulk materials. So why does surface area really matter? Let us look at an example from catalysis. Here we have hydrogen peroxide breaking down into water and oxygen. If we use a large catalyst particles, only the atoms at the surface are available to speed up the reaction. Most of the atoms inside the particle remain unused. But if we take the same material and break it into nanoparticles, suddenly the surface area increases dramatically. Now a much larger fraction of the atoms are exposed and active, which makes the reaction faster and more efficient. This is one of the main reasons nanomaterials are so powerful. More surface area means more reactivity, faster interactions, and entirely new possibilities in chemistry, biology, and energy applications. Now let us put the idea of scaling into a general mathematical form. For order of magnitude scaling calculations, we can represent an object using just a single characteristic dimension, which we shall call d. This simplifies our analysis and helps us see how properties like surface area and volume scale as size changes. For a cube with sides of length d, the surface area goes as d squared, while the volume goes as d cubed. That means the surface to volume ratio S over V is proportional to 1 over d. In other words, as objects get smaller, their surface area relative to volume increases dramatically. This simple relationship captures one of the most fundamental scaling effects, and it is the reason why nanostructure behaves so differently from bulk materials. Another key concept revealed by scaling laws is the strength to weight ratio. Think about the elephant and flea again. The flea can leap hundreds of times its body length, while the elephant can't even leave the ground. Why is that? Scaling laws give us the answer. Muscle strength is related to the cross-sectional area of the muscle, which scales as length squared. But body weight is proportional to volume, which scales as length cubed. So as animals get bigger, their weight increases much faster than their muscle strength. This means smaller creatures like fleas can lift or jump far beyond their own body weight, while massive animals like elephants are limited by gravity and their own size. Let us make the idea of strength to weight ratio more precise. The strength of a muscle, the force it can produce, is proportional to its cross-sectional area. Since area scales as d squared, we can say strength is proportional to d squared. Meanwhile, weight depends on volume, and volume scales as d cubed. So weight is proportional to d cubed. If we now take the ratio strength divided by the weight, we get d squared over d cubed, which simplifies to 1 over d. This tells us that as the characteristic size increases, the strength to weight ratio decreases. In other words, the larger the organism or structure, weaker it is relative to its own weight. That is why small creatures like fleas can achieve amazing feats of strength and agility, while massive animals like elephants are limited in their motion. We can even see scaling laws at work in human performance. This graph shows the percentage of body weight lifted by Olympic gold medalists in 2004 across different weight classes. Notice the trend. Athletes in the lighter weight classes are able to lift more than 5 times their body weight, while those in the heaviest classes lift a smaller fraction of their own body weight. Why does this happen? It is the same scaling principle we just discussed. Muscle strength goes with cross-sectional area, proportional to size squared, but body weight grows with volume, proportional to size cubed. So as athletes get bigger, their strength doesn't keep up with their increasing weight. That is why smaller athletes, pound for pound, are stronger than larger athletes. Now let us put some numbers to the strength to weight ratio. Using scaling laws, we know that strength to weight ratio goes as 1 over the characteristic dimension d. That means the smaller the dimension, the greater the ratio. Now here is the challenge. How many times greater is the strength to weight ratio of a carbon nanotube with a diameter of about 10 nanometers compared to the leg of a flea with a diameter of 100 micrometers? And how does it compare to something as large as the leg of an elephant, about 2 meters across? This sample calculation will show us just how dramatic scaling can be and why nanomaterials like carbon nanotubes are far stronger relative to their size than anything in the natural world. Let us work through the numbers. We start with the given diameters. A carbon nanotube has a diameter of about 10 nanometers or 1 times 10 to the power of minus 8 meters. The flea's leg is about 100 micrometers or 1 times 10 to the minus 4 meters, and the elephant's leg is roughly 2 meters across. Now, since strength to weight ratio scales as 1 over d, we can compare them directly by taking the ratio of their diameters. First, comparing the nanotube to the flea, the ratio comes out to be 10 to the power of 4, meaning the carbon nanotube has about 10,000 times greater strength to weight ratio than the flea's leg. Next, comparing the nanotube to the elephant. Here the ratio comes out to be 2 times 10 to the power of 8, that is about 200 million times stronger in terms of strength to weight ratio. So from elephants to fleas to carbon nanotubes, scaling law makes it crystal clear. The smaller the structure, the stronger it is relative to its weight. So far we have seen how scaling affects biological systems and materials like nanotubes. Now let us shift our attention to mechanical systems. When we scale down or scale up machines, springs, gears, or other mechanical components, the same laws apply. Their strength, stiffness, oscillation frequencies, and wear behavior all depend directly on size. In this section, we will look at how mechanical properties scale and why the performance of mechanical systems at the nanoscale can be completely different from what we expect at larger scales. Next, let us look at how mass scales with size. When we make an object bigger or smaller, its mass doesn't change in a simple linear way. Instead, assuming the material's density stays constant, mass is proportional to the cube of the characteristic length at d. For example, if we double the size of a cube, its mass doesn't just double, it increases by a factor of 8, since volume grows as d cubed. This cube scaling is critical because it shows why large structures or organisms feel much strong effect of gravity compared to small ones. Simply put, the bigger something is, much heavier it becomes relative to its strength. Among the most common forces in mechanics is gravity. At the Earth's surface, the acceleration due to gravity is about 9.8 meters per second square. The gravitational force acting on an object is simply its weight given by F equal to mass times g. Since mass scales with the cube of the characteristic dimension d, gravitational force also scales as d cubed. Now let us compare a rock that is 10 centimeters across with a dust particle that is only 10 micrometers. The dust particle is 10,000 times smaller in size, but because gravity scales with the cube of size, the gravitational force acting on the dust is reduced by 10,000 cubed, that is a factor of 1 trillion. This is why a rock falls straight down under the weight, but a dust particle can float and remain suspended in the air. At very small scales, gravity becomes almost negligible compared to other forces like air resistance or surface adhesion. In mechanical systems, two important types of forces arise from surface interactions. The first is frictional force, which resists motion when two surfaces slide against each other. We are all familiar with this. It is the reason your shoes grip the ground or why machines need lubrication. The second is striction force. This is the adhesive force that comes from molecular level contact between surfaces. At larger scales, we don't notice it much, but as we shrink down to micro and nanoscale systems, striction becomes dominant and can even cause surfaces to stick together. Both friction and striction strongly influence how systems move, how they wear over time, and how reliable they are. And importantly, their behavior changes dramatically as the size of the system changes. That is why understanding scaling is essential in mechanics. Let us now look at how friction and striction actually scale. At the macroscopic level, frictional force arises when two surfaces slide against each other. It is given by the familiar relation frictional force equal to mu f, which is the coefficient of friction, times mass times g. Since the mass m scales with d as d cube, frictional force also scales as d cube. An important point here is that friction at large scale is independent of the contact area. It depends only on the normal force. But things change dramatically at the microscopic level. Here striction, the adhesive force caused by molecular interactions like van der Waals forces, become significant. Striction force scales with the contact area, which means it grows as d square. So at large scales, friction dominates, but as we shrink down to smaller and smaller scales, striction becomes much more important, sometimes even the main force governing the behavior. As we scale systems down, something interesting happens with wear. The rate of erosion itself tends to remain roughly constant, but the amount of material available to erode away gets smaller and smaller as the size decreases. This means that the wear life, the time before failure, scales directly with the size of the system. Mathematically, wear life is proportional to the thickness divided by erosion rate, and therefore proportional to characteristic length d. The implication is striking. A device that lasts years at centimeter scale might survive only seconds when shrunk to the nanometer scale. But there is hope. At the nanoscale, atomically smooth surfaces and strong covalent bonds can dramatically reduce erosion, allowing for near zero wear and extremely long lifetimes. Now let us see how scaling laws work for springs. According to Hooke's law, the force of a spring is equal to minus k times x, where k is the stiffness and x is the elongation. Now if we assume that stiffness stays constant and elongation scales with the size of the spring, then the spring force itself is proportional to the characteristic length d. But mass, on the other hand, scales with cube of t. This means when we look at the oscillation frequency, it scales as 1 over d to the power of 3 halves. In simpler terms, smaller springs oscillate much faster than larger ones. That is why tiny mechanical systems can vibrate at extremely high frequencies. As we saw in the last slide, oscillation frequency scales as 1 over d to the power of 3 halves. Since the period of oscillation is the reciprocal of frequency, it scales as d to the power of 3 halves. Now let us consider an application question. Imagine a microcantilever beam that is 100 micrometers long and a diving board that is 5 meters long. If both are deflected and released at the same time, how many oscillations will the microcantilever complete while the diving board completes just one oscillation? To solve this, we first take the ratio of the bolt length to the microbeam length, which comes out to be 50,000. Since the period of oscillation scales as d to the power of 3 halves, we raise 50,000 to that power and get about 11 million. That means the microcantilever oscillates roughly 11 million times in that time, while diving board completes just one cycle. Now let us look at how potential energy scales in springs. From Hooke's law, the potential energy stored in a spring is given by 1/2 k x square, where k is the spring constant and x is the elongation or compression. If we assume stiffness remains constant, then elongation scales with the characteristic length d. Substituting that, the potential energy scales as d square. That means as we double the size of a spring, the energy it can store doesn't just double, it actually increases 4 times. So bigger springs can store disproportionately more energy compared to smaller ones. Now let us look at the scaling law for gravitational potential energy. The formula is Ug equals m times g times h, where m is the mass, g is the acceleration due to gravity, and h is the height. Since mass scales as d cubed and both gravity and height are constant, independent of size, gravitational potential energy also scales as d cubed. This means that if you double the size of an object, its gravitational potential energy increases by a factor of 2 cubed, that is 8 times more. So larger objects store dramatically more gravitational energy when lifted to the same height compared to the smaller ones. Now let us look at the scaling law for kinetic energy. The formula is kinetic energy equals 1 half mv squared. Here mass scales with d cubed, while velocity is not directly related to the size of the object. That means kinetic energy also scales as d cubed. So if we double the size of an object and keep the same velocity, its kinetic energy increases by 2 cubed, that is 8 times more. This explains why larger moving objects carry dramatically more destructive energy compared to smaller ones, even if both are moving at the same speed. This concludes lecture 2, where we explored how scaling laws apply in mechanical systems, from mass and gravity to friction, wear, and even springs. In the next lecture, lecture 3, we will shift our focus to scaling laws in electrical systems. We will see how fundamental electrical quantities like resistance, capacitance, and electrostatic forces, etc., change with size, and why these principles are so important in modern electronics and nanotechnology.